Okay, thank you for being back on time. You learned there was somebody saying that life is what happens while you are busy making other plans. And that means that we couldn't get Hitoshi today here with us, but he's been kind to make time anyway and deliver the lectures remotely. So he's going to give us a big picture overview on the microscopic physics at the TeV scale, and that would serve as our first theory-oriented lecture. And yeah, it's going to be virtual Blackboard, so the two things together. Enjoy. Thank you, Hitoshi. You have 1 hour.
Okay. Oh, wasn't it 45 minutes? Is it 1 hour?
Afternoon, we have 1 full hour. But
oh, I see. Okay.
Take your time. If you want to have more questions at the end, maybe you can stop at 45.
Okay. Well, I will adjust it dynamically on my way. Okay, so I don't know if Roberto told you the news that my wife had an accident while we were in Geneva. She right now hospitalized in Geneva, and I am at the hospital. And the one unfortunate thing about this, though, is that this is the University Hospital of University of Geneva. So right here, I can actually access you using EduRoam. And so that's why I'm actually here teaching online. And then hopefully, I'm also trying to mimic the Blackboard lecture that was required by the organizers. So we'll see how that goes. So I'm supposed to give you sort of the big picture of the TeV scale physics, especially in the context of muon collider. And you have been already listening to lectures or nearly 2 days at this school about specifically. So I'd like to go all the way back and talk muon and also collider, and together at the end are all. So that's the idea of my lecture. So to go all the way back, let me just get started with talking about the particle physics in general. Oops, doesn't work somehow. Ah, know what the problem is. Was working just a minute ago. But my finger doesn't work.
We can see all of your screen moving around and
Okay.
you changing apps, and we mostly can hear you fine. So,
Yeah, so
up to minor
now you
glitches
can
in the
hear me
connection seems
fine.
to be okay.
Okay. But I cannot write. Oh, now I can. Okay. Good, good, good. Now I can write. So I don't know what the problem was, but I'd like to go all the way back to what particle physics actually is meant to be, and you all know this. So here you are attending a lecture, and every one of you is made of a bunch of atoms with nucleus in the middle, electrons moving about. And the minute we actually learned this, we meaning collectively humankind, we made a huge progress because now we could understand the entire chemistry based on a single principle, right? And so we have learned a lot and could explain many more phenomena than 19th century chemists could do using modern physics. And as a matter of fact, we, first of all, but just by knowing that electrons orbit a nucleus satisfying Pauli's exclusion principle, that was enough for us to understand the entire structural periodic table, which elements have similar chemical properties because they share the same valence electrons. And more quantitatively these days, the chemists actually do use first principle calculation spatial Schrodinger equation to actually understand properties and shapes of many complicated molecules. So this is a huge success by stepping from one distance scale, namely human scale of the order of centimeter to meter, down to the atomic and molecular scale of the order of, say, 10 nanometers, 100 nanometers. Not only that we could see what the fundamental constituents are, but we could also understand many of the phenomena which was just taken for granted empirically up that point, now based and explained based on first principles. So that was a huge progress. And as you all know, we also made further progress by looking at atomic nuclei, protons and neutrons. And to understand the properties of nuclei based on the fundamental constituents here, namely protons and neutrons, is still a challenge because nuclear physics is a very complicated subject, strongly correlated systems, multi-body systems. But nonetheless, we have basic understanding based on simple nuclear shell models and stuff like this. So there again, we made a big progress. We understand how the islands of stability work in nuclear physics and so on and so forth. We now understand that the protons and neutrons are made of three quarks bound together by the gluons. And at that level, this is actually very complicated. You all know this is as an output of the physics, how the quarks are confined inside protons and neutrons. Based on that, this gives you the we understand work. What the basic constants are, and also how to explain the in and around us. So that is what particle physics was. Do more, we have to go to small delta x, and that means high momentum scale because delta p is related to delta x by de Broglie's wavelength, and high momentum, now once you're high enough, using special relativity corresponds to high energy. So that's why we need to go to high energies. And so that's the trend of what we have been following in particle physics over. We need to know what high energy, because we have to design and build an instrument that allows us to probe interactions happening at the energy scale. So understanding the energy scale is, of course, in some sense, the starting point of all discussions talking about next major facilities. And going all the way back, so we knew that there was a distance scale of about 1 meter here, and people discovered the distance scale of the order of 10 to minus the 10 meters. And this is a 10 to minus, I am actually more 8 centimeters. This is of the order of 10 to minus 12 centimeters. And size of the proton and neutrons is less than 10 to minus 13 centimeters. And this would correspond to the energy scale roughly of the order of GeV. And you all know that. And the question was, what is the next energy scale? And back in those days, when people were studying the structure of the protons and neutrons, they didn't know, except for one energy scale that was already present, the Fermi scale, that describes the interaction of the weak interaction, that's of the order of 10 to minus 5 GeV to minus 2. So if you naively take the square root inverse of this quantity, that is about 300 GeV. So at least we had some idea that something should happen around 300 GeV energy scale. Now, it was Fermi who, of course, came up with this constant that we know what energy scale is important in physics. And he, of course, talked about how this energy scale came about from interaction of the neutron decaying to electron, proton, and anti-electron neutrino. And of course, we now understand this process is actually by the W boson. And neutron contains two other quarks in it, UD, and they're spectators, they don't do anything. Here's a neutron, here's a proton, and that's the nature of the nuclear beta decay. And when you're at the energy scale much, much end up with this full Fermi interaction, and the coefficient of this full Fermi interaction, therefore, namely the Fermi constant, is related to the mass of the gauge boson, in this case, the W boson, which we have already measured to be about 80 GeV. Also depends on this couple is actually related to the W mass. Reason why W has a mass at all. So it's nothing but G squared V squared. So this actually ends up being 1 over 2 squared, where V is not the value of the Higgs boson. To the kind of energy needed to probe this energy scale directly in accelerators. And so he apparently gave get up to this energy scale to probe his energy of the Fermi energy scale. And what he designed was the size of the circumference of the accelerator, which is about the same diameter of a planet. And he will. Now that sounds crazy. Nobody would imagine a big accelerator that goes all the way around our planet at once. But that was actually a bare minimum for him. In those days, the only kind of experiments they knew was a fixed target experiment. So once you have a circular machine like this one, it's a cyclotron and synchrotron, you extract a beam, you smash that on a target, and out comes many things over here. And what's going on? Accelerated is hitting another proton in this target, and the center mass energy of the collision is only growing the original proton beam.
Hitoshi, there is a very frequent disconnection of the audio. So if there is any chance you can get another Wi-Fi, that's maybe helping, because every 10 words we get a sufficiently long jump that we suffer a little bit. So if there is any other Wi-Fi, maybe it's going to be better.
That's a...
In the meantime, I can ask if anybody remembers the cyclotrons.
Okay.
It's a Berkeley product, we understand, so I want them to know.
Thank you for reminding them. There is another Wi-Fi which is more public version.
Yes, sounds like it's the same strength, but I don't know if it's better than at Rome.
Okay, so how is this now? How is my audio now?
So far, so good. We'll see. Because at the beginning, it was kind of okay also on the other one. Thank you.
Okay. So this is a new Wi-Fi, and it's not EduRoam, so we'll see how much better that is. So I was trying to explain why Fermi had this crazy idea of the Globotron, and that was because when the only kind of experiment he knew was the fixed target experiment, and the center mass energy of the collision of a proton at rest and proton beam of energy EP goes like a 2 times MP times EP. So if we just naively plug in the kind of energy scale we think we like to probe, namely that the square root of S, just like at the case of the OHC, is 14 TeV. This is the energy of the beam, right? And then if you try to reproduce this 14 TeV over here, then energy of the proton beam turns out to be like 10,000 TeV. And if you also think about scaling up Large Hadron Collider, which is 27-kilometer circumference, to the Earth, that is 40,000 kilometer circumference, the energy you can get up to in terms of square root S is not even quite 14 TeV, but it's more like 6 TeV. And so you can see that back in those days, even if they could build a proton accelerator with the best magnet they had, which was nowhere close to 8 TeV, that you can probe energy scale barely reaching the TeV energy scale. So that was actually a necessity for him. So I'm sure he was joking talking about this, but to reach the energy scale he proposed, this was actually absolute necessity to build an accelerator that goes around the planet at least once. So this really shows the importance of development of technology, which I'm sure Daniel Schulte talked about already accelerated technology, because that is what really helps us to do what we like to do. Namely, that when, instead of doing the fixed target experiment, now we build a collider where beams are circulated in the opposite direction and they collide head on in their center of momentum frame. So that's why we can now achieve 14 TeV of center of mass energy just by having only 27-kilometer collider. So going from here to there was, of course, a huge development, which allowed us to get going in doing particle physics and make progress out of it. So I hope this is just the first example of demonstrating why development of accelerator technology is really what brings us forward. And now that we're doing the LHC, so one development people are talking about a lot in Europe these days is go to FCC with a 91-kilometer tunnel. But just making bigger tunnel is not good enough, because if you like to get up to even higher energy scale, reaching up to 80 something TeV or so, you need to place a magnet on its way. And 8 Tesla, just by simple arithmetic, enough. So you need to have a magnet that goes up at least 14 TeV, and people even dreamed of going up to higher magnetic field. So getting up to high energy not only requires a new tunnel, but also a much more powerful magnet whose technology we don't have at this stage yet. So that requires additional development of accelerator technology. But in addition, I'm sure you heard about the other options too. So in the case C minus machine, building a circular collider would be a problem, because whenever you bend the electron beam along the side, the shape of the tunnel, they would radiate synchrotron radiation, and energy per turn for the synchrotron radiation goes like 1 over r times energy of the beam of the mass of the particle to the fourth power, which is nothing but the gamma to the fourth. So if we have a light particle like electron and trying to get up to multi TeV energy scale, this is already a big ratio. So getting up to the something like 350 GeV with this 91 kilometer tunnel for E plus E minus center mass energy, which is the idea of SCCEE, which is already reaching the limit of the synchrotron radiation. Not only the synchrotron radiation, of course, causes a lot of damage in the accelerator, and so you have to shield it, but also the fact that beam keeps radiating and loses energy basically means that E plus E minus machine of this size, even though it's as big as 91 kilometer to suppress the synchrotron radiation, is such as you can put all of your power, electrical power, into maintaining the energy instead of actually accelerating the energy. So that is a huge power consumption people talking about, reaching more than 300 megawatt of the electrical power. And that is especially a concern in these days in environmentally conscious citizens. So that's why the E plus E minus machine in a circular tunnel is really reaching the limit. The FCCE is probably the last one we can ever think about. And that's why in the case of E plus E minus, people have been talking about a linear machine, because once we have a linear machine, basically the curvature is infinite. It's linear. So, the straight line by definition has a radius of curvature infinite. So there's no synchrotron radiation. That's why you can use full energy from the acceleration all the way into the collision energy at the center. And that was one way to go. But with this kind of technology over something like a 15-kilometer and the size, you can still lead up to something like a 500 GeV. So that in this case, the best the requirement of the technology is really to come up with a accelerating cavity, which can produce a high what is called a gradient, And best cavity developed for International Linear Collider is something like 35 megavolts per meter. So once you know what energy you like to reach for a charge E, that is the case of electron, you can do the math and compute how much length is needed for the entire tunnel. And that's why you end up with something like tens of kilometers in this case. So if you can come up with a higher gradient acceleration technique, that could, of course, make the accelerator shorter. That's another development people are talking about today. And for example, something called a plasma accelerator, plasma wake field accelerator, is an idea that somehow you have some material in here and you produce a plasma so that the positive charge and negative charge are dislocated from each other. And you may be able to actually create such a plasma using the particle beam or using laser, whatever technique you might use. The whole point here is once you have a plasma, then you have a strong electric field from separated positive and negative charges. And once you actually put the beam at the top of this electric field, then the electron, they get accelerated this way. And that can actually achieve much higher acceleration gradient, like 10 gigavolt per centimeter. So that is something that is being studied right now, but that is still very futuristic. And that's talk of a future. So that I hope that we can still keep working on that idea. But nonetheless, this has not been actually achieved yet. Hence, we are talking about the muon collider. So in this case, once again, the synchrotron radiation goes like energy over the mass to the fourth power. But now you have mu instead of me, which is something like 200 times higher. And 200 to the fourth power is a big number. So you can really, really, really suppress synchrotron radiation compared to electron machine. And hence we can at least talk about it. And what people are talking about these days, I'm sure you have seen this parameter, that the side of the radius of the wing may be 10 kilometer. In the case of the US design, people were talking about, because that would barely fit into the Fermilab site, so that we can actually use the existing facility to actually host such a machine in principle. And even though this is actually much shorter compared to FCCEE by a fact on an order of magnitude in terms of the radius, that this larger mass of the muon really helps us to reduce synchrotron radiation. So hopefully that is still manageable. And of course, we have heard all the challenges about the fact that this is actually a short-lived particle, because the muon lifetime is only 2.2 microseconds. So you have to produce muons, collect the muons, put them into the beam, cool them enough, and put that into the storage ring, the acceleration ring, and bring them up to a TeV kind of energy scales, everything before they decay. So that's the huge challenge. But once they get sped up to a TeV energy scale, time dilation helps them to live longer. So that's why we can be in business of actually circulating muon beams thousands of times inside a ring of like 10 kilometers in the end. So that's why we are talking about this here in this school. So I mean, in all of these cases, we had to rely on all this development and technology by really, really smart accelerated people. So I really appreciate what they do, and we have to help them and count on them and design on the future machines. And for that, as again, I have to emphasize again, we need to know what energy aim for. So now I'm going back to the TeV scale. So why do we talk about TeV scale still in these days? Well, we have already reached the energy scale. In the center of quark, gluon, partner center mass energy, TeV scale have been already reached at the Large Hadron Collider. We have discovered Higgs boson, 100 GeV. So why are we talking about electroweak scale again? And for a very simple reason, we have not understood mechanism of electroweak symmetry breaking. So we draw this potential and talk about electrosymmetry breaking in the standard model. But if you just write down this the potential, it really looks like a toy model. It does the job, but it looks kind of like a cheesy toy. And that's the feeling many people had in the end. And that is partly because of the fact in the case of superconductor, we see in the laboratory, we know the slab of superconductor would repel the magnetic field. That's an Meissner effect. And if you actually look very closely into it, you may punch through it if it's a type 2 superconductor. And what that means is that there's a characteristic distance scale called the penetration depth, which describes the distance, how much the B field can expand within a piece of superconductor. That may be something like a order 100 microns or something. So it's a microscopic distance scale compared to the size of a piece of superconductor. So in this case, we learned that this happens because there is a condensate with electric charge. Sorry, there's a condensate with charge -2, which has an expectation value. And once you have this condensate or charge 2 object, that would actually produce a mass for the electromagnetic field because of the usual kinetic term. A kinetic term contains the vector field in it by the covalent derivative. And once this y acquires a mass, and that is actually the mass of the magnetic field inside superconductor. So that's how we understand this short penetration depth in a piece of superconductor. So that is basically how the standard model has been modeled by example of the condensed matter physics. But in this case, this charged to condensate is not an elementary particle, but is actually a Cooper pair of 2 electrons. And the way we write down the Lagrangian is very much the same, except for this time derivative piece. So it looks very much the same. And that is what is called the Ginzburg-Landau Lagrangian of superconductivity. And here is the chemical potential, which is meant to be positive. So if you just remember the fact that Lagrangian is the negative of the potential, this is really the Y model potential we always draw in the standard model. Is the same potential, as a matter of fact. And using this potential, it occurs an expectation value and hence gives rise to the finite mass of the magnetic field. So that part is exactly the same. But in this case, we have a deeper understanding because this field that acquires an expectation value of charge -2e actually made of 2 electrons. And we also understand how 2 electrons are bound together. That is because of the exchange of the phonon due to lattice deformation. And then, in principle, you can compute, for example, what this mu should be, what lambda should be, and therefore what this length scale of the penetration depth should be. And then theory becomes predictable or predictive, rather. So this is the more microscopic explanation that will give you more predictive power. And that is the BCS theory of superconductivity. And I'm sure you have all seen this somewhere else. And we have not reached this level of understanding. So we mock the fact that electroweak symmetry is broken, and that's why there is the mass for the W boson. That's why W boson is short range and goes over only like we know we assume free symmetry is indeed broken. And as one of the first tests of this idea, we have just managed to produce an excitation that can swing around in this direction, which is called the Higgs boson, right? But this is only the first step. And the reason why that is only a first step is because here we could understand superconductivity very well because we knew what this condensate was made of, two electrons, and what actually created a condensate to exist due to the instability of Fermi surface by this phonon exchange between the two electrons on the Fermi surface. And that understanding led to a predictive theory, but we haven't gotten there yet. And that's why, at least in the past, before you guys were born, we theorists talked about all kinds of other ideas, just right, rather than writing this toy model of the Ginzburg-Landau type theory, to go to something more fundamental. And at the end of the day, there were basically only two directions people talked about. And one of them is called Technicolor. Oops. So the idea of Technicolor theory is to remind ourselves that in the standard model, what you need is to break SU2 cross U1 to U1 QED. But you may also have of this idea called custodial SU2, that the standard model tangent actually has a slightly bigger symmetry if you just focus on the Higgs sector. That U1 hypercharge is embedded inside another SU2, and UR QED at the end of the day is embedded in this SU2 vector. And that is because the Higgs field contains charge plus component and charge zero component. But in addition, you know in the standard model, you need to define yet another combination of the fixed field, which is made of the complex conjugation and switching two components around. So this is phi plus star. This is phi zero star minus. This combination has the same SU2 doublet property, but has the opposite U1 hypercharge. So this one has hypercharge plus 1/2, but after conjugation, this one has hypercharge minus 1/2. And without having both of them, you can write down all the Yukawa couplings where you use this top version to write down Yukawa coupling for the up-type quarks, while this bottom version to write down Yukawa for up-type, down-type quarks or charged leptons. So you actually use both of them. And it turns out that when you actually put both of them together into a single multiplet, so if I write this one first, oops, I got the sign wrong. And put them into a 2x2 matrix, this neutral one acquires an expression value. And now you can see that this is actually breaking the symmetry of a multiplying SU2 matrix from the left and right. But if you take both of them together, this identity matrix will commute with them. So you have this SU2 vector left. And that is what is called custodial SU2. And that guarantees that the W is the same as mass of the Z boson times cosine theta W. And I can talk more about that if you're interested. But nonetheless, this is the structure we already know in the standard model. And that is perfectly embedded into this SU2 cross SU2 bigger symmetry called the custodial SU2. oops, SU2 symmetry. And I erased this by a mistake. Okay, so that's something we know that should happen in a standard model. But the idea of Technicolor is to remember that that is exactly what happens in QCD. So just imagine that you have two flavor QCD with up and down quarks, and not to be confused with the standard model quarks, I'm writing them in capital letters here, and just assume that they are massless. Then the QCD Lagrangian has SU2 left plus SU2 right symmetry, because up and down quarks, because they are massless, can be split into left-handed and right-handed Weyl fermions, just like fermions in the standard model. And you can rotate left and right independently from each other. And that's the symmetry we do talk about as a chiral symmetry in QCD theory. So here we are specializing this to tech QCD. And this QCD is now Technicolor theory. But the same idea, you have some SUN gauge group under which you have two quarks up and down, so that you have this SU2 left cross SU2 right symmetry. And in the case of the standard model QCD, we know this chiral symmetry is spontaneously broken because there is a condensate of UU bar and DD bar, and that breaks the chiral symmetry again down to the diagonal subgroup SU2 vector. So we know this does happen in QCD. As a matter of fact, if you actually look into some of the early papers in Technicolor, people talked about using QCD to generate the mass of the W boson too. So that didn't work out because energy scales are too different from each other. But at least you can at least think about it, because QCD does exactly what the standard model is supposed to do, namely to break SU2 cross SU2 symmetry down to SU2. So that actually brought people to the idea that maybe that the way standard model breaks the electroweak symmetry is by the scaled up version of QCD, namely Technicolor. It's just that the QCD happens at the energy scale of GeV or something, and this Technic QCD happens at 1,000 times higher energy scale. And that is a beautiful idea, because that would dynamically explain why SU2 cross SU2 symmetry has to be broken to SU2 vector, rather than just setting up a potential like this one, which really looks like a toy model to many of us. Unfortunately, this attempt totally failed, and this idea is completely dead. And let me just tell you quickly what the issues have been. So the idea is that you have this U and D doublet, both for left-handed and right-handed. And under SUN Technicolor, they transform as the fundamental representations, like color triplets in the case of QCD. So we're just literally scaling that up to the TeV energy scale. And under SU2 left, here's the doublet. This is singlet. Under SU2 right, this is singlet. This is doublet. And that's it. But then we have to think more about how exactly this theory would work. So when Q left and Q right forms a condensate to break SU2 cross SU2 to diagonal SU2, first of all, we need to make sure that this theory is internally consistent, namely free of all the gauge anomalies. And there's something Ed Witten pointed out, that if you have an SU left SU2 gauge theory with odd number of doublets, the theory is actually anomalous and inconsistent. The number of doublets needs to be even. So that tells you that MTC has to be even. So the lowest gauge group you can think about is SU4. Again, you can ask the question, what about SU2? That actually happens to have another problem. So I'm not actually getting there yet, but if you have any questions, let me know later. So SU4 gauge theory with doublets for left and right is a perfectly viable the QCD-like theory, which is believed to break higher symmetry. So everything seems to work out. So what went wrong? Well, it turns out that in the case of the standard model, not only the Higgs generates the mass of the W boson, that's how you generate the mass of the W boson, right? So you generate the mass of the W boson, but in addition, you need to generate the fermion masses is the phi twiddle we talked about on previous slide, so that it can generate both the up-type quark masses, down-type quark masses, and also the charged lepton masses. So you need to have these couplings. But here, we basically replace the Higgs by this fermion bilinear composite object. So what you need then is that you have left-handed standard model object, like quarks, right-handed standard model object in the standard model as well, somehow coupled to this Q bar Q in a technicolor sector. And that is dimension 6 as a for fermion operator. So it's suppressed by some energy scale. So you already know that in this theory, you expect the fermion masses to be relatively small. And that idea worked for a long time until the top quark was discovered and found to be something like 133 GeV, which is not light. This is the heaviest elementary particle we know of today. So the idea that top quark actually was discovered was already a big problem for this technicolor theory. In addition, this fulfillment operator, just like in the case of the neutron beta decay, presumably needs to be actually blown up into a UV complete theory. So this actually needs to be made.
Hitoshi, just to tell you that Google tells us in 15 minutes the call is self-destroying. So,
Oh, okay. But in 50 minutes, we're supposed to finish, so that's probably
yeah,
okay.
including some question which may arise. Maybe
Okay.
I'm able also to
Yeah.
get a new call, but just to make sure if you can wrap
Yeah,
up
okay, I got
before
that.
that deadline. Thank you.
Yeah, I hope to finish in 2-3 minutes, so that I hope is fine. So at some point, you need to actually open this up to make it a UV complete theory. So instead of having some effective operator, you would like to actually make it into a real propagator of something. But minute you do so, you need to write down a UV complete theory. So all of these operators that were meant to produce these Yukawa interactions, they alone, I exchange the same objects in between. And those four fermion operators among standard model fermions ended up producing very large flavor change neutral current effects, like the KK bar mixing, BB bar mixing, the K long decaying to mu plus mu minus, and so on and so forth. So that actually turned out to be unacceptably large. So even though the mechanism was beautiful, because of too large flavor change neutral current effects. And even later, it died once again because of the electroweak precision observables. Because when you look at so-called oblique parameters in a vacuum polarization diagram like this one, well, to be specific, this is called the S parameter, which is a mixing between the third component of SU2 gauge boson and U1 hypercharged gauge boson over here. And this parameter would pick up contribution out of these technicolor quarks in there. And I already told you that because the color, the technicolor has to be at least 4 and bigger, so there are actually at least 4 of them inside this loop diagram. In addition, because these things are supposed to condense due to strong interaction effect. This was actually pinched into a row-like resonance that enhanced the effect even. So it turned out that this was excluded by the precision measurements of this kind of oblique parameters of electric symmetry, electric precision observables, namely this S parameter. In addition, top quark was discovered, and that actually turned out to be very heavy, as I mentioned already, despite the expectation that is suppressed by the heavy energy scale, whatever that is, by the 1 over lambda squared. So that was also against expectation in this theory. So Technicolor theory died at least 3 times. But the reason I'm talking about this is not just about talk about this story of a dead theory, but because this actually demonstrates the idea that you would like to get to more fundamental understanding of what's going on in the standard model. And Technicolor is an attempt to do so. And I told you already that attempt failed. But this is what we eventually would like to reach. So instead of talking about this Landau theory of superconductivity, which is just a toy model, which gives you all the right features of phenomenology, in the case of superconductivity, we have a one step deeper understanding of what's going on. And Technicolor was meant to give you that deeper understanding, but it failed. And so what I would like to talk about tomorrow is talk about yet another attempt, which tried to do the same thing. That is actually supersymmetry. And you might say, well, this one is dead too. I have to point out it's not dead. It's just that we haven't found supersymmetry up to the energy scale we have probed so far. But we would like to understand what's going on with that as well. So let me review what supersymmetry was meant to be about, because these days I understand most students and postdocs don't study supersymmetry at all. So I'd like to give you just a snapshot of what that is, and then try to see how that would connect to the grand picture of electric symmetry breaking. And I'd like to also emphasize tomorrow, even without talking about these specific ideas like supersymmetry or Technicolor, at least there's something we have to do to get a better understanding of the mechanism of electroweak symmetry breaking. And that is the measurement of Higgs self-coupling. So at least we need to do that. And we haven't done this job yet. So the reason why we're talking about the electroweak energy scale still today is because we haven't finished the job. And in order to finish the job, we need to go to higher energies beyond what we managed to probe at the OHC and soon with the high Lumiere OHC. And that's why we're talking about going up from, say, 10 EV, TeV kind of center mass energy scale to something like 10 EV scale in parton center mass energy, and hence the motivation for the muon collider, or possibly other collider options I briefly mentioned earlier. So anyway, so that's the way I like to describe more about the mechanism of electric symmetry breaking tomorrow. So I stopped here so that hopefully we can finish questions and answers before Google tells us to get out of here. All right, let me stop here.
Thank you very much, Hitoshi. Questions from the audience? I have one in the back. Just 1 second.
One question about the motivation of muon collider, because if FCC can probe 80, nominally 80 TeV, but we are interested in 10 TeV, why the need to build a muon collider?
Okay, that's a good question. So that is the major difference between, more generally speaking, between hadron colliders and lepton colliders. And the proton machine is a hadron collider because proton is one of the strong interacting particles, generically called hadron. And muon collider is a lepton collider because muon is a lepton, just like electron-positron. In the case of the lepton collider, when particle like electron and an antiparticle positron come in, then they collide at the center of mass energy scale and can produce objects that would reach basically the energy of the beam itself. So if we have one TeV plus C minus, then electron and positron have half TeV each, and you can produce a pair of half TeV object, barely, but roughly speaking, half TeV object in pairs, and you can really probe that energy scale. But in the case of hadron collider, like proton-proton collider, proton is made up of 3 quarks and gluons binding them together. And especially as you go to higher and higher energies, then each quark inside the proton carries less and less energy because of the additional gluon emission. And the gluon, already from the beginning, has much lower energy compared to the energy of the proton as a whole. So roughly speaking, the best interaction you can hope for is that you can extract, let's say, a quark out of this proton at about a third of the energy of the proton, and extract another quark out of this proton, also at about a third of the energy of the proton. If they collide in the middle, collision probes about a 1/9 or about a 10th of the energy of the proton-proton collision. So even if you may have 80 TeV proton-proton collision, you are probing the collision of the partons inside, like quark or gluon, only at the level of 10 TeV or even far less than that. So that is the major disadvantage of the hadron collider. And that's why building a lepton collider whose energy is roughly speaking about a 10th of the hadron collider would probe exactly the same physics at the end of the day. Does that answer your question?
Yeah, this answer, thank you, but there is no motivation to probe higher energy than 10 TeV, so FCC is not enough?
If you think the FCC-HS is given, maybe you don't want to talk about muon collider. But we don't know that. So as I mentioned already, building a high-field magnet has proved a very difficult process. And I don't know if anybody mentioned this. And of course, the other people are much more expert than I am about these things. So I can't actually say anything bad about it. But when I went to talk to people who are building this niobium-3 and tin magnet, you have to put niobium and tin into an oven that they can get chemical synthesized. When they come out already as a niobium-3 and tin, you can't touch it. It's so brittle. I asked the engineer how brittle that is, and he said, "Oh, Hitoshi, it's like dried spaghetti. If you touch it lightly, it breaks." So you're dealing with this very difficult material. And you put just loads of epoxy on top of it to make it solid enough that you can first touch it to begin with. And you can never change its shape anymore. You can wind the cables made of niobium-3 tin. So actually going up to the scale of really making sure this craftsmanship people use to build this magnet today can be scaled up on an industrial the scale and build enough of them to fill up the entire 91-kilometer tunnel seems to be a really daunting challenge to me for a non-expert. And it's not clear at all to me if that is actually achievable on several decades time frame. And a close friend of mine, Akira Yamamoto, is a specialist on superconductor cavities, not magnets. But he gave a speech at the Granada meeting 6 years ago for the previous Western European strategy discussion. And he gave us this ballpark figure that to go up 2 Tesla in magnet field, then you need to spend 10 years of R&D. And right now, we barely reached the 12 Tesla magnet for the triplet for the Hailumi upgrade. So there's still some ways to go. So that's why I am myself, people have different opinions about this, but myself, I'm not taking FCC-HS for granted. And that's why it's still worthwhile to talk about different possibilities that might reach up to the same energy scale. And if that actually turns out to be feasible, we may actually even realize that kind of other flight options even earlier than FCC-HH, and that will be incredible for everybody. So that is the reason why I am personally interested in muon collider as a direction for the future.
Okay, thank you.
Does that answer the question?
Yes,
Okay,
yes,
good.
perfectly. Thank you.
Thank you for answering, Hitoshi. So we have 2 minutes. I may ask if you can stay for a little longer or you have to rush, because then I could
I
try.
can stay longer, yeah. So do we just need to